Recall that the posterior probability function is given by this. Let's say our training data is z1, y1 through zn, yn. The y values are either 0 or 1. The probability of the observed data, is given by the product of the probabilities that y equals to 1 for those zi whose y value is 1, and the probabilities that y equals to 0 for those zi whose y value is 0. That is the product, the probability that y equals to 1 given that x equals to zi, for all of those I where yi equals to 1, times the product of the probabilities that y equals to 0 given that x equals to zi over all of those I such that yi equals to 0. Since the probability that y equals to 0 given x equals zi is the same as 1 minus the probability that y equals to 1 given that x equals to zi, we can rewrite the product as this. So here we have the probability that y equals to 1 given x equals to zi, and this part becomes 1 minus the probability that y equals to 1 given x equals zi. Okay, and now this we can just rewrite it as p of zi. And this part, the same thing, so we get 1 minus p of zi. Now, we want to find estimates for beta 0 through beta p that maximize the probability of our observed data given by this product here. Let L of beta 0 through beta p be the product p of zi times the product 1 minus p of zi, like this. Okay, this is called a likelihood function. Thus, to find estimates for beta 0 through beta p, we want to maximize the likelihood function. Letting beta be beta 0 through beta p, we can rewrite the likelihood function as L of beta given by this product. So here we just replaced beta 0 through beta p by beta. Recall that p of x is given by this, so p of x depends on the parameters beta 0 through beta p. Okay, to indicate this dependence, we'll write p of x semicolon beta for p of x. So L of beta is the product of p of zi semicolon beta times the product 1 minus p of zi semicolon beta. Maximizing the likelihood function is the same as maximizing the log of the likelihood function. Okay, so let capital L of beta be the log of little l of beta, which is the log of this product. Okay, this is called the log likelihood function. We'll try to maximize the log likelihood function, capital L of beta. Note that L of beta is the sum of the log of p of zi plus the sum of the log of 1 minus p of zi. Okay, we just broke up the log of the product into a sum of logs. Okay, and that's equal to this, the sum of yi log of p of zi plus 1 minus yi log of 1 minus p of zi. Okay. Here, so when yi equals to 0, then what counts is this part. And if yi equals to 1, then what counts is this part. So that's why we can rewrite it this way. Okay, and that's equal to this. If we just combine the terms with yi in front, so we would get this. So yi times all of this. Okay. Now, look at this part here. We have log of p of zi minus log of 1 minus p of zi. Okay, we can rewrite this as log of p of zi divided by 1 minus p of zi. Okay, but note that p of zi is e to the beta transpose zi prime divided by 1 plus e to the beta transpose zi prime, where zi prime is given by this vector, 1 zi1 through zip. Okay, so 1 minus p of zi is given by this, and p of zi divided by 1 minus p of zi is given by this. It's a simple calculation. Okay, so going back here, we can replace this part and this part. So we get this. Okay. Now, log of e to the power beta transpose zi prime, that's just beta transpose zi prime. Okay. And this part becomes log of 1 minus log of the denominator. So we get this here. Okay. So L of beta is given by the sum of all of this here. Okay, so we have a nice formula for the log likelihood function, L of beta. To maximize L of beta, we will use the multivariate Newton-Raphson method. Okay, let's look at how the method works, and we'll return to L of beta.